let's talk about diarrhea. It turns out that there are quite a few side effects to chemotherapy. It can include constipation and it can include diarrhea. And it turns out that in many cases diarrhea wins. With diarrhea, there are a number of ways that you can overcome that, and in particular is a drug called loperamide HCl. And this is the active ingredient in Imodium, and this is not a sponsored segment, but if you wanted to get the same thing for significantly cheaper, the generics are exactly the same thing, and I happen to have a Kroger brand generic here that does the job quite well. Loperamide HCl turns out is an opiate, but not the fun kind of opiate. No, it's a very big molecule, so it cannot cross the blood-brain barrier, so you don't get a high from it. All it does is constipate you the same way that any other opiate would do. So while you're on chemotherapy, you can either develop a drug habit or you can take the active ingredient in Imodium, the loperamide HCl, 2 milligrams. And so this stuff will plug you right back up. Now, it occurred to me while I was thinking about this particular video that a little bit of physics may be in order. And so the first case that I want to talk about is Newton's second law of motion, which many people have learned is force is mass times acceleration. And it turns out that that's not entirely correct. You will see this in textbooks that it's mass times acceleration, but that is a simplification. That's assuming that mass doesn't change. And in the case of explosive diarrhea, it turns out that mass does change. And so if we consider diarrhea as a propulsion mechanism, explosive diarrhea specifically, then let's go back to the actual Newton's second law that says that force is a change in momentum. So what we have here is some funny symbols here. The d by dt part, the d in the numerator and the dt down here in the denominator, this is in fact not a fraction, it's a derivative. It's a change of something over time. And that something happens to be momentum. So momentum is the thing that we need to be concerned about here, and momentum is just mass times velocity. Momentum has a direction. Velocity has a direction as well as a magnitude. And so if we actually consider the momentum as mass times velocity and we plug that back into the force equation, then force is the change in momentum with respect to time. In the case of this equation, what you then have to do is consider each thing changing with respect to time. You can either have a mass that changes times velocity over time, or you can take a velocity and multiply that by a change in mass over time. And so the actual full equation is that you'd consider both cases. So we're going to consider a very simple case. The first thing we're going to do is consider that we have straight line motion, in which case we can take our vectors off because we're also going to consider that we're moving at constant velocity. So whatever amount of mass is coming out the backside of you, that's coming out at a steady rate, and I can confirm this is true, and this can then propel you forward as a means of propulsion. So if we assume that the velocity is constant, then that means that it doesn't change with respect to time, and that means that this whole term right here can go away, and all we have to consider is the velocity times the change in mass, and that's the amount of mass that you're expelling out your backside. So in the simplified Newton's second law that applies to not only rocket propulsion, but it turns out explosive diarrhea, the amount of thrust that you can get depends on the tiny bit of mass that you're expelling out your backside at whatever speed you're expelling it out your backside. So it's the change in that little bit of mass over time, and that will then give you, by Newton's third law, propulsion in the opposite direction. So mass goes out the back, and the rocket, or you, go out the front. And so here we are, explosive diarrhea as a means of propulsion explained in terms of rockets and Newton's second law.